on. Let me just see if I can manage these buttons. And yeah, there it is. Okay. So,
yeah, we see it.
I'm going to put it in full screen mode. I don't know if it's full screen for you. Okay.
Yeah, it is.
Is it fine?
Yeah, it's good.
Okay, okay. Okay, thank you. So I'm going to talk about some of our recent work on using operator theoretic approaches to distributed generalized Nash equilibria. And I'm going to stress in as much as possible the aspects that relate to extending this approach to different scenarios and the flexibility it offers, as well as the elegance, in my opinion. So basically, I'm going to say that this general work is a direction that has been followed in recent years, and it's inspired by the prevalence of applications of game theory over networks, from demand response management in smart grids, resource allocation in cloud computation, cognitive radio networks, all sorts of applications that essentially involve games with some coupled constraints. So one example that I put here is a rate control game over wireless ad hoc network, where some users transfer data through their chosen path, and each decides their own data rate. But each link has a maximal capacity, as seen in here. So we essentially have a linear couple constraint. Each user minimizes its own cost that depends on its utility and the data rates to the unit delay. So essentially here we have this coupling through the maximal capacity. Another example is a network Cournot competition, where several firms are supposed to produce goods that allow them to access different markets, and each market has a certain capacity. So the firms have to balance the production costs with the pricing, as well as satisfying this market capacity. Essentially, in here, it's also representing a case where, as we're going to see, some of the costs involved might be quadratic, which would correspond to what Giancarlo would have as an affine pseudo gradient. So the general framework is a game that involves a set of players, each with their own objective function, that is coupled through their other decision and through the coupled constraint. And the coupled constraints are affine, as linear as you're seeing here. The equilibria point is then characterized by what's called the generalization of the Nash equilibria. So generalized Nash equilibria, where this non-unilateral deviation of each players from the optimality has to be feasible. So it has to be lying into this X set. In terms of types of methods for solving GNE computation in these classes of scenarios towards distributed. So there have been, obviously the standard way is to develop rather centralized methods where the data of all players is collected by a center, but also master-slave methods where each player keeps its local cost and set actions, but a master node coordinates their computation because of that coupling constraint. And in recent years, many researchers have looked at distributed or center-free methods, and those are particularly useful in scenarios that involve those type of ad hoc networks, peer-to-peer networks, where there isn't any center. The local data is kept by each player, and only local communication is permitted over some communication graph, as you see here in the bottom left. And essentially, the players can share information bidirectionally, And this means that one has to involve some communication graphs described in terms of adjacency matrix, incidence matrix, and so on. Essentially, the main condition for this communication graph is that it has to be connected. And the simplest one is to assume that it is undirected, and this is what I'm going to assume here. So when I said that in recent years, I've put here just a sample of the type of recent work in this context. A lot has been first developed in the context of Nash equilibrium computation and distributed, which means without coupled constraints. And one of the first works was by Koshan, Elich, and Schambag, and Svensson, Carr, and Xavier. So that's 5 years ago. But very recently, a GNE, generalized Nash equilibria in games with coupled constraints, have been started to be looked at. And here I put some of the works. Now, what I'm going to talk about here is essentially an operator theoretic approach that essentially allows one to develop such distributed GNE algorithms and to achieve convergence with fixed step sizes. Because the goal would be to essentially have something that hopefully can go over some of the drawbacks of diminishing step sizes, which is typically the case that's used in terms of maybe making the algorithms converge faster. So this is the goal here. And an operator approach is particularly suited, and it's very nicely allowing one to do that. So the standing assumption is going to be, again, convexity of each cost with respect to their own action, differentiability, as well as a non-empty interior of X, which essentially translates in those constraint qualification being met. And if one takes the KKT analysis to look at the equilibria conditions in terms of defining some local Lagrangian and a multiplier, one gets to see that the conditions at the bottom of the page are equivalent to having each of the players solving their own optimization problem. The key observation here is that each has a different local shadow price or a different multiplier lambda I here, yeah? And this is different for the common network resource because the constraint here in one are actually common. Now, a refined solution is what's called the variational GNE, where the KKT is in terms of a common multiplier, lambda star. And this is in terms of the same conditions as you see here to the left, but just having a single such common multiplier or shadow price. And this is essentially representing this variational GNE, which has been shown to have economic interpretation of no price discrimination or equal penalty to all of the players for using these coupling constraints. In a compact form, these conditions in 2 to the left can be put in terms of just defining a pseudo gradient, the F that essentially is similar to what Giancarlo had defined as the G. So the stack vector of partial gradients of each cost function with respect to their own action. And the compact form of that also involves the coupling constraint matrices AI. So this is shown in the relation 2 to the right, yeah? And also the normal cones of the action set of each players and the normal cones of the multipliers, which is the positive orthant. So essentially, what we're going to want to do here is to have a distributed algorithm that converges to a variational GNE, which means satisfies these conditions too, and for which we can show convergence with fixed step sizes. Now, this is where the operator theoretic comes into play, because those KKT conditions too can be even further put in a more compact form as saying that they represent the condition for finding 0 of an operator that can be split into the sum of 2 operators, A and B. So essentially, the two operators are shown here representing the normal cones, as I was talking about, as well as the matrices involving the coupled constraint. And then the other operator is involving just the pseudo gradient. And this type of splitting is not the unique one, obviously, but this is what I'm going to use in here. And it allows one to essentially separate the condition in terms of the gain properties, which is the pseudo gradient F, and the constraint properties described in terms of the matrix A. And now one can use different operator splitting methods to find zeros of a sum of operators, and essentially the conditions are that these operators are monotone, and this is what we're going to assume. And one of the most common methods is the forward-backward method that essentially allows one to express the necessary condition for finding a zero, as in equation number 3. Yeah. And based on this, use a Picard-Banach fixed point iteration to develop an algorithm that essentially involves two operators, what we call the forward operator involving the B and essentially the pseudo gradient, and a backward operator. And standard operator theoretic results in, for example, in Gaussian combat will show that under the condition that A is maximally monotone and B is co-coercive, this makes the two operators average, and it can be shown that this iteration converges with appropriate step sizes. So this is a relatively elegant, compact way of showing, as long as those conditions on the two operators, A and B, are met. And essentially, if one then puts together the player-wise, the element-wise component of such a forward-backward splitting operation, one essentially ends up with just a primal dual projected gradient, as in this relation 5. Where essentially what one sees is that each player has to do a projected gradient that involves its own cost function, as well as the pricing, yeah, as well as a projected ascent on this pricing that has to be done by some center, because you see here the distributed, this is with respect to each player only in the first equation. So this is the case in which some of the recent work by Grammatical has essentially looked at developing and showing convergence for a center having to actually operate and implement this second equation, and then broadcasting that information to all of the players in the first. And then as long as they have full decision information on the others, and this is the x minus I that you see here in blue, then this can be actually shown to converge with fixed step sizes tau and sigma that are going to ensure that the properties for co-coercivity of B are met. The key is because of this separate the splitting that we have here, A is essentially a linear skew-symmetric under normal cone operator, so the monotonicity is going to be met automatically. So the difficult part is just showing this co-coercivity. And this can be shown under strongly monotone pseudo gradient. So it's not just the monotone as Giancarlo had. Now, what we're going to talk about here is essentially how can we extend this to the case in which we do not have a complete graph. In other words, each player does not have access to all of the others' actions, as in 5, but only a partial decision information as resulting from communicating only with some neighbors over a communication graph. And this is the case that one has here, where each player only knows and communicates with some of their neighbors. There is no central node to disseminate. So one way in which this can be solved is essentially to allow each of them to build an estimate on the other's decision by communicating with neighbors. Yeah. And this estimate is going to have the superscript I, so it is going to be bold, and this is going to be essentially the estimate of the other decision. And all these estimates then are going to be appended to their own decision, and each variable that each player is going to have is going to be essentially this bold X superscript I, which essentially should be basically the same, because this represents the profile of all agents' action. At the same time, the multipliers, each player is going to be endowed with a multiplier lambda I that should be also be the same, so that they converge to a variational a GNE. So the goal here is that there should be achieving a consensus. Yeah. The assumption on the communication, as I mentioned, is just that this is undirected and connected. It has a weighted Laplacian L, and one extra thing that we're going to introduce, in addition to these local estimates on the decision and the copy of the dual variable, is an auxiliary variable Z that helps to satisfy the coupling constraints and to reach consensus. So what I'm going to put next is the extension of the primal dual algorithm to this connected communication graph, non-complete. And these four equations are basically the extension of what we have. And what this is, in a nutshell, is, first of all, a generalization that's involving each player using a projected gradient play that involves now only the estimates of the others. And you see here that in the first equation, it's the bold X superscript I, which means that each player just uses the estimate. Then there's going to be an equation that adjusts those estimates. And the idea is that because they want to achieve a consensus, so they're going to just update it with the discrepancy between their neighbors with a correction that's added to this projected gradient plane. And then the last two are actually the equations for updating the dual variables lambda. And again, this is just a generalization of the one we see initially based on the center, just so that actually they achieve a consensus based on local communication. Yeah? So there's going to be discrepancy between the neighbors' dual variables, as well as this Z variable that essentially plays the role as if a discrete integration. Now, what I'm going to show next is that this algorithm is nothing more than the algorithm that results from applying a forward-backward operator splitting to a pair of doubly augmented operators A and B. In other words, taking that framework that elegantly the operator theory provides and just augmenting it to deal with the fact that we have to reach consensus on the estimates of the other's action on the dual variable for variational GNE. So the first step is to put this whole in the stacked form that's involving the pseudo gradient. But now this pseudo gradient, you'll notice that involves the estimates. And this is the bold X that you see here. So everything is bold because of that reason. Also, this is involving some augmented or weighted Laplacian, again, because of the duplication, as well as the matrices A and B that are going to be the extension. And you're going to notice that A is just a diagonal and B is just a column vector. Now, taking this stacked form, one can even write it more compactly in terms of those two W augmented operators, yeah, and show that essentially this is just a precondition forward backward. So what you have here at the top is the standard way of doing it. These A and B operators are the ones that we see in the classical forward backward splitting. Instead of these, we're going to consider the bold A and B operators defined as follows. And I'm going to give the intuition what it is. So I'm going to start essentially from, first of all, the B. The B is going to be involving the pseudo gradient. And here is going to have the extended pseudo gradient with this R matrix that essentially is the one that either selects actions or zeros one. So it's just so that we maintain consistency. On top of that, it has a linear term that's involving the consensus, the Laplacian matrices for the estimates and for the dual variables. For the A, instead of the normal cone, we're going to have the augmentation of those normal cones, and they're going to be in terms of the dual variables and primal variables, augmented estimates of them, as well as this skew-symmetric matrix that now is going to involve, again, the matrices augmented, but also the Laplacians. Yeah. And the key is that we're maintaining the skew symmetry for the A operator, which means that monotonicity is going to be easy to show. But then what is going to be difficult is to have a way in which we can show co-coercivity of the operator bold B, as well as a way in which we can actually realize the distributed operation of the backward step. But the first result that shows in this theory one is that with these doubly augmented operators, the zeros that one gets are essentially at the consensus, on the consensus space, or where all of the primal variables are equal, all of the dual variables are equal, and moreover, where this X star and lambda star correspond to a variational GNE pair. Yeah. So this is the first important result. Then in terms of actually showing those properties, the first thing is that we're going to introduce a preconditioning matrix or a metric matrix that is going to enable one to have distributed operation. And here what I'm going to say is that instead of the normal forward backward, in which you have here at the top, one requires the resolvent of the operator A to be computed explicitly. Here, I'm going to introduce a matrix phi. Yeah, so this is as if I don't use identity, but a matrix phi. And this is equivalently showing to the left here in the middle, where now I have a resolvent of a preconditioned operator. And by properly selecting this preconditioned matrix, one can actually have this backward operator, this resolvent, computed explicitly in a distributed manner. And to do that, this metric matrix that we introduced is shown in red. Yeah. And one can see that basically this is a symmetric matrix. We essentially need it to be positive definite so that it is also acting as a metric matrix. And we're going to essentially use a norm induced by this metric. But the key property is that when one uses this special metric matrix with the matrix that was skew symmetric that was appearing in the A operator, one obtains as a result this lower triangular matrix here at the bottom, which allows one to explicitly compute the backward step because of this lower triangular form. So if one then uses the resolvent operation for the normal cone in terms of the projection, this gives exactly the form stacked that I put in the beginning. So essentially, this is showing that.
Lacra, sorry to interrupt. You have 5 more minutes left.
Yes, I will just take 2 more minutes.
Yeah, sure.
So with this definition, one then can have ways in which one can see how can we achieve those properties that we need in terms of the A being monotone, which is simple, but B also be co-coercive. So the standing assumption that we're using is that the extended pseudo gradient that we have, this is the new entity that we've introduced, is Lipschitz. Yeah, so this is a relatively mild condition that one was. So under that condition, we can show that not only is A maximally monotone, but B is beta coercive, with this beta depending on what? On the strongly monotonicity of the game property from the beginning and the Lipschitz, and the maximal weighted degree of the communication graph. And then we can actually have some properties for the precondition operators phi inverse A and phi inverse B under the induced norm, and that's why we needed that phi to be positive definite. And then one can use the standard Gaussian-Combet results in terms of T1 and T2 being average, and can get convergence to a generalized Nash equilibria, as in this theorem 2, where one can show that with appropriately selected step sizes that essentially can be realized in a distributed manner, each of the players has their own estimate converge to a value that is the same and is a variational GNE. And the estimates, the convergence of all of the dual variables to the same corresponding optimal dual variable. So this is just the general framework, but I can tell you that we've expanded it to address different scenarios, because this is what I see the beauty of an operator theoretic approach that unifies the setup. We've been looking at cases in which the algorithm is not necessarily synchronous. So it can be asynchronous and with delayed information. We've been also looking at ways in which maybe we can make the algorithm more efficient, so that instead of keeping all the estimates of all of the players, if I have some structure in the game, maybe I can actually reduce the size of that estimate that each player has to do. In other words, just to conclude, I think that this is a very nice and elegant framework that offers many interesting options of actually addressing some of the recent directions in this area. So I'm going to stop here. Thank you.
Thank you very much, Lacra. Are there any questions for the speaker before we, Dr. Kane says, what is the maximum number of agents that can reasonably be handled numerically right now?
We have had examples with 100 agents. The algorithms and the proofs are irrespective of the agents, the number of agents, what's going to make a difference. Mathematically, everything it's working out. What's going to make a difference is when one tries to actually apply these, you get into how much is the what's the size of each player's state space? Because if we have 100 agents, each has to keep 100 entries variables. Can we reduce that? So theoretically, this can be scalable to any number of agents, but practically one has to think of ways in which this can be made more efficient.
Just a quick follow-up from Dr. Keynes. He's asking, what about handling an infinite number of agents?
No, this is under the assumption of finite number of agents. Yeah.
Okay. All right. Thank you very much. I do not see any more pressing questions. Thank you very much.